In chapter 1, we looked at a lot of different methods for evaluating limits. The first thing we always try is plug the number in and hope that you get something that's not indeterminate, but frequently we did have indeterminate forms. So what we're looking at today is another method for evaluating limits that are of indeterminate forms. I've got a link here that if I have not shared it with you before, this is a good time to do it. Let me go ahead and show you what's on this page. So this is it's called Paul's Online Notes. I don't know if you can see the whole thing here, but that's all right. Paul Dawkins is a math professor at Lamar University, and he has very graciously shared all of his notes. Let me see if I can, there we go. All of his notes for the classes that he teaches, which we can go in here and look: algebra, calc 1, 2, 3, differential equations, but then there's also this extra stuff. And there's actually a lot of really, really good resources here. There are written out explanations, there are examples, and there are solutions and practice problems and such. So if you would like to use this as a resource, I would recommend it. Also, we've got these cheat sheets where he kind of puts a whole bunch of things together. This limit one right here is the one that would be good for reviewing, just to make sure you remember all of the different procedures that we learned before. So I would suggest that you look at this one. Okay, I'm going to go back here though. Move this back down. Okay. All right. So we are looking at indeterminate forms. The most common indeterminate form that we ran into when we were evaluating limits is we would end up with a 0 over 0, or sometimes a positive or negative infinity over infinity. Either infinity could be positive or negative. And then there's some other ones as well that we did see a couple of them, but not very often. One of them was infinity minus infinity, because remember, it depends, which infinity is bigger or which one is approaching infinity bigger, that sort of thing. 1 to the infinity is an indeterminate form. 0 to the 0th is an indeterminate form. And infinity times 0 is an indeterminate form. Let's see. 1, 2, 3, 4, 5, 6. We're missing one. Infinity to the 0th is also an indeterminate form. Okay, so we've got 7 different indeterminate forms here. We are primarily going to be dealing with forms that look like these two, okay? There are other methods for evaluating some of these other ones. A lot of them involve logarithmically rewriting, or maybe algebraically rewriting the expression until we achieve one of these two, but these are the two we're going to focus on here, okay? And we are going to use something called L'Hopital's rule, okay? Say it out loud. L'Hopital, not La Hospital, L'Hopital. All right, you'll notice I have it spelled 2 different ways. That's on purpose, up here and right here. One of them is a more modernized version of French. Somebody in French, you can correct me if I'm wrong, but I'm pretty sure this one is the modernized one and this one is the old one. Okay, either way, it doesn't matter. When we say it, we say L'Hopital, not La Hospital. Okay, so if we are evaluating a limit at a point, and that a value can be either a number or it can be infinity or negative infinity. Okay, it doesn't matter. If we're evaluating a limit and we have a fraction, we have f of x over g of x, okay? And one of 2 things need to occur. Either both the limit of f and g have to be equal to 0, or the limit of f and g have to be positive or negative infinity, okay? In other words, I either have something approaching 0 over 0 or infinity over infinity, okay? Then the limit of the original quotient is equal to the limit of f prime over g prime. Okay, so we can't say that a limit is equal to 0 over 0 because a limit exists, 0 over 0 does not, okay? But if the limit on top and bottom are both zeros or both infinities, then L'Hopital's rule says we can take the derivative of the top, the derivative of the bottom, and apply the limit of those derivative functions, okay? Please notice this is not taking the derivative of f over g, because if we take the derivative of f over g, what rule do we have to use? Correct? Quotient rule, okay? This is not the quotient rule. So we're not taking the derivative of this function, we're taking the derivative of the top and bottom function separately. Okay, so what do we need to do in order to use L'Hopital? We must capitalize, underlined, look, I'm even circling it, it's important. we must indicate that the condition for L'Hopital has been met. We need to show that the limits of f and g are both either 0 or an infinity. Okay, so we are going to write that first. Okay, we're going to check by plugging in this case it's 0, and we're going to say yes, the limit of the top is 0, the limit of the bottom is 0, therefore L'Hopital applies, and then we have this new form. Okay, so let's look at this first one. Right now, if I plug 0 in, I'm going to get 0 minus 0 plus 0 over 0 minus 0, so it's definitely approaching 0 over 0. I cannot, don't write this down, I cannot write 0 over 0. This is something that the College Board calls a linkage error. If you do this, you will not get credit for whatever the point here is, because this does not exist, but this limit on the left side does. So this is a false linkage. Okay, so it's a linkage error. Don't write that. What we can do is we can say, hey, the top and bottom both have limits that are going to approach 0. So we can say the limit as x approaches 0 of x cubed minus 3x squared plus x, notice I'm using parentheses because limit applies to the whole thing, is equal to 0, and, let me make this a little bit bigger, and the limit as x approaches 0 of x cubed minus 2x is also equal to 0. Now, you might be looking at this one and saying, I don't need a new rule because I can very quickly see that x factors out of the numerator and denominator, and then I can cancel that out using that algebraic method we've learned before. But this is just another way to do it, and I'm starting with a simple one, okay? Because the algebraic methods don't always work like we would hope, or sometimes they're pretty complicated. Think back to when we had to rationalize numerators, when we had like root x plus 2 minus 4 and stuff like that. Okay, so because this is a 0 in the numerator and denominator, then this original limit, okay, so therefore this is equal to the limit as x approaches 0 of the derivative of the numerator, 3x squared minus 6x plus 1, over derivative of the denominator, 3x squared minus 2. Okay, and I probably should have arranged my space a little bit better, but now I can plug 0 into this and I get 1 over negative 2, so negative 1/2 is my limit. Okay. Again, you may be looking at that saying, hey, I can just factor out the x, but I'm showing you another method for how to evaluate these so that we don't have to use all that algebra. Okay, for the next one, again, the first thing we try with limits is plugging in our constant. So 4 times 0 over sine of 0 is 0 over 0. So I'm clarifying, or I'm writing explicitly that the condition has been met. So limit at 0 of 4x is equal to 0, and the limit at 0 of sine of 2x is also equal to 0. Therefore, by L'Hopital, this is equal to the limit as x approaches 0 of the derivative of 4x, which is 4. The derivative of sine of 2x is 2 cosine 2x because we used the chain rule. The derivative of sine is cosine 2x, and then times 2. Okay, now when we plug 0 into this, we get 4 over 2 times 1, which is 2. So our limit is 2. We could also have obtained that by using the limit as t approaches 0 of sine t over t theorem and doing some rearranging, but now we don't have to. Okay? All right, it'd be a good idea for you to pause and maybe try the next couple. Okay, for this one, we're doing the limit at infinity of e to the x over x squared. If I plug infinity into e to the infinity, I get infinity. And same thing in the denominator, infinity squared is infinity. So we have the conditions met for L'Hopital. So limit as x approaches infinity of e to the x equals infinity, and the limit as x approaches infinity of x squared equals, nope, not 0, infinity. Therefore, by L'Hopital, this is equal to the limit at infinity of the derivative, e to the x, over the derivative of x squared, 2x. Okay, now plug infinity in again. Once again, I have infinity over infinity. All right, so you guessed it, we're going to apply L'Hopital again. Limit as x approaches infinity of e to the x equals infinity. Limit as x approaches infinity of 2x, also infinity. So once again, the limit as x approaches infinity of e to the x over 2. Now when we plug in infinity, we get infinity over 2, which is just infinity. And that's my answer. Okay, so L'Hopital can be applied more than one time if the conditions are still met. Okay, and on that one right there, no amount of algebraically reducing or rewriting or anything like that would have allowed us to evaluate that. We maybe could have done it logarithmically, but that would be a mess. Okay, last one of this type. So let's plug in 0. So we have 1 minus cosine of 0 is 1 over 0 plus 0. So again, we have 0 over 0. Okay, so L'Hopital applies. So we have the limit as x approaches 0 of 1 minus cosine x equals 0, and the limit as x approaches 0 of the whole quantity x squared plus 3x equals 0. Therefore, by L'Hopital, this is equal to the limit as x approaches 0 of 0 and then plus sine x over 2x plus 3. Okay, now you might be thinking, hey, we plug 0 in again. We still get 0, so let's use L'Hopital again. No. We do get a 0 in our numerator, but we have a 3 in the denominator. 0 divided by 3 is just 0, and my limit is 0, okay? If I would have tried to do L'Hopital again, I would have, don't write this down because it's not right, I would have ended up with cosine x over 2, and then I plug 0 into that, and I get 1/2, and that is not the limit, okay? So if you try and apply L'Hopital again when the condition is not met, it does not work. You will not get the right answer, okay? All right, a couple more examples. Now we're going to use a graph and a table, okay? So here we are looking at the graph of f of x. This is f of x. And we are trying to evaluate the limit at 3 of f of x over x squared plus 9. If I plug 3 in, I get f of 3, which is 0, over 3 squared minus 9 is also 0. Okay, so L'Hopital does apply. I'm going to write my conditions being met down here. So limit as x approaches 3 of f of x equals 0, and limit as x approaches 3 of x squared minus 9 equals 0. Okay, so then by L'Hopital, this is equal to the limit at 3 of f prime of x. Doesn't matter that I don't have an equation for f. I can still take the derivative, and then over 2x. Okay, so f prime of x, derivative of x. When we hear derivative, we think what? Yep, slope and rate of change. So the slope at 3, okay, the slope right here is -2. Over 2 times 3 is 6. So my limit is -1/3. Okay, maybe pause and try the last one if you haven't already. Okay, here we have a table of values for some differentiable functions f and g. We are looking for the limit at 2 of f of x minus 4 over g of x times x squared. Okay, so limit, we'll come down here, limit as x approaches 2 of f of x minus 4 is equal to f of 2, 4 minus 4, which is 0. And then the limit at 2 of g of x times x squared is equal to g of x, which is 0, times 2 squared is 4. So still 0, so L'Hopital applies. Okay, so let's come down here. So therefore, by L'Hopital, limit as x approaches 2, so I'm taking the derivative of my numerator, is going to be f prime of x minus 0 over, what do I need to use here? Yep, the product rule. So I have g prime of x times x squared plus g of x times 2x. Okay, and then now evaluating that, f prime of 2 is equal to -2. G prime of 2 is 3 times 2 squared is 4 plus g of 2 is 0, so I don't care about the 2x. So we end up with -2 over, actually, let's just reduce these. Come on, pen. So we get -1/6. And that's L'Hopital's rule.